Saxon's Trigonometry Lesson 10, Part B, is about rational denominators. Now, rational means that I can have a decimal that either ends or begins a repeat pattern. And if it is not ending or repeating, it's considered irrational. And in math, we have decided, now mathematicians in the past have decided that denominators should not be irrational. They should be rational, meaning end or repeat in the decimal. So they show you exactly what they mean. They do a few things here at the beginning. So they say like 111 divided by 99 is 1.1212, and so on and so on and so on. It keeps repeating. So that's a repetition. That would be considered rational. It could be written as 1.12 with that repetend bar. Looks like a segment marking, but you get the idea. So whatever's underneath that is the part that is repeating over and over and over. So that's repeating. 13 thirds goes to 4.3 repeating. So it means 4.333, and it goes on and on and on. Okay, so it is also rational. Pi, however, we abbreviate it down to the 3.14, but it is 159, and this continues. And the book shows you a long line of numbers for pi. There was a computer back when computers first started that was tasked with finding it, and they found that pi went to more than 1,000 digits without repeating, and then the computer could not calculate it any further. The same thing happens with the letter E, and I don't know that you dealt with it much in Algebra 2. We will definitely here in the Trig book. But it is 2.71 is about where we usually approximate it, but it continues 8 to 8, and just like pi, you see that it goes on and on and on and on. These are irrational. Nothing's repeating and it is not stopping. So we do not want denominators that would have a pi or an e in them. All right, so the same thing happens when we go into square roots or fourth roots, fifth roots, whatever kind of root. We consider anything within a root that is not like square root of 4 that goes to 2, but if it's square root of 5, that does not stop, repeat very quickly. And so if we have a root in the denominator, we need to fix that. And the same thing with the I, imaginary. They are not rational. They are irrational because they are imaginary. So I can't have roots and I can't have i's in denominators. So this section is all about fixing those. So example 4 is 4 plus root 3 over 2 minus 3 root 3. So I can't have that in my denominator. And so I need to multiply it by something that will fix it. What mathematicians discovered was that if they change the sign in the middle and they do the same thing, whatever you do to the bottom, you must do to the top to keep it the same. When they distributed, they lost the radical in the bottom, and that's what they wanted. So let's start with the denominator part to show you how that's working. So we are basically treating these as parentheses that we are distributing. 2 times 2 is the 4. 2 times 3 is 6 root 3. Negative 3 root 3 times 2 is negative 6 root 3. And negative times positive is negative. 3 times 3 is 9, and root 3 times root 3 loses the root and keeps the 3, so it's going to be 9 times 3 there. Before I move on and fix this, notice that this is a positive and this is a negative of the same thing. What will they do? Cancel each other off. Why did they do that? Because we changed the sign. We forced this to be the pattern every time. This is why we wanted to do what we did. Change the sign, forces the terms in the middle to go away. So I will often shortcut and not even bother to do the middle terms because I know they're going off. So in the FOIL part, I would keep the first and the last only and ignore the middle. This will always cancel off. That's the whole point in changing that sign. Okay, so now before I finish the bottom, I'm going to go ahead and distribute the top. Again, we're treating them as parentheses and we're distributing out. 4 times 2, 8. 4 times the 3, 12 root 3. Root 3 times 2, and 3 root 3 and this root 3. So the 3 is still on the outside, and root 3 makes a 3. All right, now we can simplify. So 8 and 9 make 17, plus, these are like terms, 12 and 2, 14 root 3. And in the denominator, 9 times 3 is 27. 27 goes with 4, 31. And now I look to see, can I reduce all of the outside numbers? 17, no, it's a prime, it's not going to reduce. Just a second, I'm checking that answer. This was example 4, right? Did I miscopy or did I mismultiply? My denominator's wrong. Oh, that's a minus. Minus 27. Yikes. Negative 27 minus 4, 23. Negative 23. Ah, that's looking much better. Okay, so can I reduce 17, 14, and 23? Well, no, 17 and 23 are both primes. They're not going to reduce. Now, it shows you can have all of these signs different. If you don't want the denominator to have a negative, you can change everybody's sign. Not critical one way or the other, although technically in math, they try to avoid the negative in the denominator and put it for the numerator. So you could write it minus 17, minus 14 radical 3 over 23, and that would be the same thing. But you get the idea there now. All right, example 5. 2 minus I cubed plus 2I to the 5th over negative 2I plus 4. Okay. I see several things here immediately. One, I've got an I in the denominator. I want to treat that the same way I did the root and get rid of it by changing the sign. Here's my problem. Changing the sign in the middle of this one will not help me because it is the I need to eliminate, and the I was written first. So I want to rearrange this to actually be in the correct order before fixing the denominator. Now I can put it as 4 plus 2I, same thing, top and bottom, to keep it in balance. And I didn't say this before, but when you multiply something that is the same top and bottom, that's the equivalent of a 1. If you multiply a concept by 1, you have not changed its value. And that's why you can do this without changing the problem, but putting it in a format that is acceptable. Okay, so before I can do this distribute here, I've got a mess here of I cubed, I5. I need to simplify this down as far as I can. Okay, so this goes back to our I chart where you had I means the square root of negative 1. I squared is just keep the inside contents, negative 1. I cubed adds an I with this and makes it negative I. I to the 4th is doubling this to a positive I squared, which was negative 1. So a negative 1 is positive 1. Wait a second, I feel like that's wrong. No, it's not. I had the same problem last time. I to the 5th adds an I to that, which starts repeating the pattern. Okay, so now that we're there, what is I cubed? Negative I. So negative times negative I is going to make this plus I. And I to the 5th is going to make this I. so it's basically 2i. So like terms I and I, so this whole top should become 2 plus 3i over, and I'm going to put this in the correct format, 4 minus 2i, and we are distributing that with the 4 plus 2i and the 4 plus 2i. So now the problem's in the right format, and I can do the distribute as I need to. Starting with the denominator, just because I usually like to, 4 times 4 is 16. I'm going to forget the middle terms because I know they're canceling off. Negative times positive is negative. 2 times 2 is 4. I times I is I squared. And I'll come back and fix that in a minute. Distributing, 2 times 4, 8. 2 times 2, 4i. Negative 3i times 4 is positive 12i. And 3 and 2 makes 6i squared. Now let's simplify these things. 4i and 12i make 16i. I squared is negative 1, so this is negative 6. 8 minus 6 is 2, and that's 16i. In the denominator, I squared is negative 1, so this is 16 minus negative 1, so plus 1, denominator of 17. Uh-oh. I've made a boo-boo somewhere again. I'm going to pause while I figure out where that is, and then I'll tell you. Yeah, that was an easy catch once I saw it. It was right here. It was negative 4 times negative 1, and that should have been positive 4, so it should have been 16 plus 4 is 20. That's much better. Now, can I reduce all of those numbers? Most definitely by 2. So this drops to a 1 plus 8i and a 10. You can leave it here, or you can separate it as they did into 2 different answers, which is 1/10 plus, and then they reduce that 8/10 again. I'm okay with it staying here, but if you separate it, then that reduces down to 4/5 I, and that's why they separated it, because they could reduce that down one more time. All right, I'm going to do completing the square in another video because it is a little work intensive.